Okay friends, welcome to the lecture 47 of Advanced Steel Design course. We are continuing to discuss about the M factor for different cross sections. So, in this lecture we are going to learn M factor for circular section and few more geometric shapes. Okay. So, this was the circular section what we considered. Look at the screen and we said that V is a point where the strip is being measured from the plane of reference, and we have derived the equation, written the equation for dA and so on. We will continue from this point and work ahead. So, we know that MA is integral y by r plus y of dAA. Now, I can rewrite this as, look at this figure, y can be simply said as V minus r, is it not? So, I replace it. So, V minus r by V dA of A, which gets split into integral dAA minus r integral 1 by V dA. Okay. So, this will now become MA is A minus r times of 1 by V dA of A. Now, dA by V integral A is integral, because dA already we have an equation with us here, 2 r square cos square theta d theta. Let us use it here. So, 2 r square cos square theta d theta by r plus y, because V is r plus y, okay, d theta. Now, since I have changed the variable, I have to change the limits as minus pi by 2 to plus pi by 2. Even r should also be changed as minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by r plus r sin theta. You can see that y is also expressed in terms of theta as you see here. Okay. So, now I get dA by V integral is minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by r plus r sin theta. We will take this equation forward. So, let us say introduce a variable k as a ratio of this r by r. Let us imagine and understand what is r by r. Look at this figure. R is a radius of curvature of the initial level of the unstressed curved beam, whereas small r is a radius of the cross section of the circular section. Okay. So, there are two different things here, and r by r will be a very large number, because r compared to small r will be very large. Okay. So, now integral dA by V will become which is 2 r square cos square theta d theta by r plus r sin theta, now will become minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by kr plus r sin theta, which will now become minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by r times of k plus sin theta, which is now two r of minus pi to plus pi by 2 cos square theta can be expressed as this value divided by k plus sin theta. Okay. Now, let us find the simplified value of this expression. Let us do that. So, let us divide 1 minus sin square theta, 1 minus sin square theta by k plus sin theta. Okay. So, if I say minus sin theta, this becomes minus k sin theta minus sin square theta. I change the sign, this goes away, then I get 1 plus k sin theta. Okay. So, I should say plus k times of, so I should say k square plus k sin theta. I change the sign again, so this goes away, so I got 1 minus k square. So, what I am trying to do here is, in simple terms friends, if I have 5 divided by 2, I should say this is 4 and 1, then I can write 5 divided by 2 as 2 plus 1 by 2. Okay. This 1 is here, okay, and so on. So, similarly, I can now write 1 minus sin square theta by k plus sin theta as, so 2 is this, so k minus sin theta plus, reminder, this 1 minus k square by k plus sin theta. Is that okay? So, therefore, my division, my integral is going to be 2r of minus pi by 2 to plus pi by 2 k minus sin theta plus 1 minus k square by k plus sin theta of d theta. Is that correct? Let me draw a line here. So, now the integral is going to be 2r of minus pi by 2 to plus pi by 2 k minus sin theta d theta minus 2r of minus pi by 2 to plus pi by 2 k square minus 1 by k plus sin theta d theta. So, we call this integral as I1 and this integral as I2. Okay. Let us do that and find out these values. You know, I1 is 2r minus pi by 2 to plus pi by 2 k minus sin theta d theta, which is actually equal to 2r times of k theta plus cos theta minus pi by 2 to plus pi by 2, which will now become 2r times of k of pi by 2 plus pi by 2 plus cos pi by 2 minus of cos minus pi by 2, which will now become I1 as 2r. This gets cancelled, okay. This gets cancelled, 2r of k pi is my I1. Let us try to find I2, which is integral of minus to plus k square minus 1 by k plus sin theta d theta. So, let us first evaluate integral of d theta by k plus sin theta, which is minus pi by 2 to plus pi by 2. Okay. This is of the form integral minus pi by 2 to plus pi by 2 dx by a plus b sin x, sorry, which is given by 2 by root of a square minus b square tan inverse of a tan x by 2 plus b by root of a square minus b square. Limits minus pi by 2 to plus pi by 2. Similar to this, I can now write 2 by root of, as a is k and b is 1 and x is theta. So, a square minus b square. So, k square minus 1 of tan inverse of a is k theta by 2 plus b is 1 by root of k square minus 1 pi by 2 plus and minus, okay, which will be equal to 2 by root of k square minus 1 tan inverse of k plus 1 by root of k square minus 1 minus tan inverse of minus k plus 1 by root of k square minus 1, which will be 2 by root of k square minus 1 of pi by 2. So, now I can say integral dA by b is I1 plus I2, that is what we have here, is it not? Integral dA by b is actually I1 plus I2. I1 we already have with us and I2 we just now had. Okay, let us do that. It is going to be 2 pi r k minus 2r, this 2r here, see here, okay, plus 2r here, 2r of k square minus 1 anyway numerator, k square minus 1 the root of k square minus 1, okay, 2r of pi, which will become 2 pi r of k minus root of k square minus 1. So, we know k is r by r. So, which is going to be 2 pi r of r by r minus root of r by r square minus 1, which will become 2 pi r of r by r minus root of r square minus r square by r square. Okay. So, dA by v integral is 2 pi r minus root of r square minus r square. That is what we have. Okay, r gets cancelled, right. So, now MA is integral dA minus r integral dA by V. So, MA in this case going to be pi r square minus r 2 pi of r minus root of r square minus r square. So, now I can find M as 1 minus r of 2 pi by pi r square r minus root of r square minus r square, which will be equal to 1 minus 2r by r the whole square plus 2r by r square of root of r square minus r square, that is M for a circular section. So, if you know the values of r and r, one can find M. So, it is a geometric property, right. So, now I can find E as M by M minus 1 of r. So, MA is integral dA minus r integral dA by V. So, MA is A minus r dA by V. So, M is also 1 minus r by A integral dA by V. This equation 2, equation 1, okay. And therefore, E is M by M minus 1 of r, which will be equal to 1 minus r by A integral dA by V by 1 minus r by A integral dA by V minus 1 of r, which is equal to E r times of 1 minus r by A integral dA by V minus r by A integral dA by V, which says that E will be r times of minus A by integral dA by V plus r. Okay, or otherwise E is equal to r minus E by integral dA by V. So, already we have dA by V computed, which is equal to 2 pi r k minus 2 times of 2 r of k square minus 1 pi by root of k square minus 1, which is otherwise equal to 2 pi times of r minus root of r square minus r square after substituting for k. So, therefore, E now becomes r minus A by integral dA by V, which is equal to r minus pi r square by 2 pi r minus root of r square minus r square. So, therefore, E is r minus r square by 2 r minus root of r square minus r square. So, if you know r and r, you can find E. Okay. So, now I know the modified cross section M, I know how to locate the neutral axis from the centroidal axis, because that is what E is. E is the offset of that. So, all are geometric properties now, is it not? Let us do one more example. I will say this as example 3. Example 1 is rectangular section, example 2 is circular section. We will go for a T section. So, let me draw the figure of a T section. Let us say this is my plane of reference O. This dimension is B1 and this dimension is B2 of the T section. Let us say it has got a centroid axis passing through this point. This is my CG. I locate a strip at a distance y measured from the CG away from the center. So, I will call this value as R1, this value as R2, and of course, we know that this is R, radius of curvature to the centroid. We call this as R3. Okay. Now, let us cut a section. Let us say this is my dV and this is at a distance V from the plane of reference. Okay. So, we know the equation MA is given by integral y by r plus y dA for the whole area. So, which will be, from the figure one can see V minus R will be y, is it not? So, V minus R will be y, R plus y will be V dA. So, which will be integral dA minus R times of 1 by V dA. Okay. Which is equal to A minus R times of, talking about dA, we have to have two parts of this. One is varying from R1 to R2, which is this piece. Other is varying from R2 to R3, which is this piece. Okay. So, I should say R times of B1, because this piece is width B1 and varying from R1 to R2. See here, varying from R1 to R2 of dV by V minus R times of varying from R2 to R3 is B2 dV by V. So, now EMA is equal to A minus R times of B1 of logarithm of V, which is R2 by R1 minus R B2 ln of R3 by R2. So, M now is 1 minus R by A of B1 ln R2 by R1 plus B2 ln R3 by R2. This is 2. We also know that E is Mr by M minus 1. Let us compute E. So, by substitution E will become R times of R times of 1 minus R by A ln of, sorry, B1 ln of R2 by R1 plus B2 ln of R3 by R2 divided by 1 minus R by A, because you know there is a denominator M minus 1. So, M is there, 1 minus R by A B1 ln R2 by R1 plus B2 ln R3 by R2 minus 1, this goes away. So, I get E as R times of minus 1 by R by A of B1 ln R2 by R1 plus B2 ln R3 by R2 plus 1. Okay. That is my E. So, I can locate the neutral axis. So, E is going to be R minus A by R minus A by B1 now. Same, I am just writing this equation. B1 ln R2 by R1 plus B2 ln R3 by R2. So, friends, you can see from this equation E, M are all functions of cross section. Okay. They are geometric parameters. Is it not? So, for a given value, let us say, for example, I will just draw this figure again. For B1 as 100 mm, B2 as 20 mm, R as 1000 mm, R1 as 500, R2 as 520, okay. So, you need to find actually R, capital R, so CG. So, you must know this dimension, which will be actually, I should say, R2 plus y bar. You can find out this. for B1 and B2, and for this dimension which is h bar, which is taken as 70 mm, one can find R. Now, all dimensions are known, one can find M, one can find E. So, once you locate E, you will be able to locate the neutral axis, and then you can find the stresses and plot the stresses. Okay. So, friends, in this lecture we learnt how to find the modified area property and the offset of the neutral axis from the centroidal axis for different cross sections. We did for circular, we did for T section. We already did for rectangular section earlier, okay, for first principles. I think there will be no difficulty in handling these kind of problems, and my reference book also gives you the MATLAB program to find out the stresses for various cross sections for curved beams. I strongly promote that you should use this textbook and download the programs and use MATLAB intensively for computing the stresses and the cross sections of these shapes for curved beams of large initial curvature, which is Winkler-Bach equation. Okay? Please do that. Thank you very much. Have a good day. Bye.